today. Plenty of topics. We'll talk more about sampling and frequencies and more patterns and aliasing and anti-aliasing and why distributed ray tracing solves all these problems. And essentially, for many algorithms, if you are not sure how to do things properly, just let's do it randomly, pick some random number and flow with the results of the random generator. And then after talking more about more patterns, we'll talk about other application of distributed ray tracing. We'll see some really cool effects that we can get with the same technique. Nothing to do with ray tracing specifically, but more of once we get used to distributed ray tracing. Distributed or randomness just means that instead of sampling at the middle of the pixel, I'll sample at a random point inside the pixel. Or instead of dividing the pixel into 9 equal blocks and sample exactly at the center of such an equal block, every such sub-pixel, instead of sampling exactly in the middle, I'll move by some random amount, but inside such random sub-pixel, and taking the results from every such sub-pixel, that is shooting a ray. The ray hits an object, namely I'm sampling the 3D scene at some points determined by the location of the pixel, and takes the results, and it's all, I got 9 results for the same pixel, and then I'm somehow taking the average color out of all these 9 samples. But the exact location is somehow at random. And then we got into the more pattern, and I thought that more pattern is such a cool topic, so I'll tell you more about it. So let's talk about spatial frequencies. Correct the spelling mistakes that I'm doing. And the spatial frequency would be if I'm moving how many changes of color per change of 1 centimeter in the image. How many times did I switch color if I'm moving from P into P1 and the distance between P to P1 is 1 centimeter in the image, or 10 pixels in the image? How many times did I move from one color of the real image, or the 3D scene? This is just sampling from this 3D world, from the 3D world. How many times did I moved in the real image, in the real 3D scene? If I would sample it infinitely densely, how many changes do I have per 1 unit of length? Similar to the frequencies that you have in the annoying sounds that you hear in the background. Okay, so that would be a very hand-wave definition of what is a spatial frequency. It's very hard to identify with my poor accent between spatial and spatial. So I'm trying to highlight that spatial is from space versus spatial. If hopefully you can decrypt it. So and bad or / interesting and definitely incorrect results occur when the sampling frequency and the spatial frequency have a simple relationship between them. I think that this is as vague sentence as I ever wrote. we check the sampling and the way we sample the world, we are shooting arrays that hit the world every 1 centimeter distance-wise, and somehow the real world behaves nicely with respect to it. That sounds very, very vague. So let's remind you of this image where we took an image of this building that has some special frequencies. The bricks has white background between the red bricks, and there is some special frequency both on X and Y. And you see this pattern that appears over here, blackish and whitish, darker and whiter region, in some relationship because the frequency of the bricks and the frequency by which the pixels are centered are nicely correlated. And that's a real image. That's what could definitely happen on your camera. And let's see a cooler synthetic example. So Moyer patterns, I think that Moyer accordingly was a waver or a knitter somewhere in the 16th century that started to notice that we are looking at two meshes and put them on top of each other, interesting things happen, interesting patterns that definitely don't occur in the original images. For example, here I have one grid of vertical line, another grid of vertical lines, vertical segments, and I put them, and you see, and definitely you don't see any more patterns yet. But if I'll take this grid and say, you know what, this is like how frequent I sample between them. And right now, you're only getting the same frequency over here. But now I'm slightly changing the sampling rate. I'm changing the frequency of one of these grids, but the other one stays the same. And you see these three vertical lines that appears right here, some frequencies that we'll understand in a second, and we'll see how it's related to the annoying noise. It's even cooler if I'm changing the gap between the grid and these strange, what's called Moyer pattern, appeared somewhere, and of course they are moving according to this sampling change. But that's all in 1D, so it's not very exciting. Let's take this grid, put it outside, and let's take the similar grid. Now these grids are of the same frequencies. All I did was the green and the blue are the very same grid. Green and blue are the very same grid, except that one is of some angle to the other. This grid consists of unit widths green, white, green, white, green, white. The same goes for the red, and I'm putting the green on top of the green on top of the blue. Sorry, then up to real estate. Putting the green on top of the blue when they are oriented at the same direction. Nothing interesting happens if I'm just slightly, think about it as your camera is not aligned. Your camera is not aligned with the world, and you see these more patterns showing up, these strange lines that appear. Again, and they appeared far away from each other. The frequency between these white lines that suddenly popped up is much larger than the frequency between these two guys. And we'll see the math of it in a second. One more example. Yeah, I'm not over speaking about it, just two concentric rings. Maybe you see, maybe you don't. Depends. Maybe I need to zoom out to see it. Now you see it. these curves over here that are definitely not curve of the original image. Another example. Here I have a grid of a greenish square, whitish square, greenish square, whitish square, etc., all the way to infinity. This grid is unit apart from each other. The green points are where I sampled this grid. Again, this is where I place the pixels. And these pixels are at distance s, there is some parameter s, that I can control how far away these points are. And now I place them again, but the gap between these 2 points is not 1. What happens if the gap between the sample points is exactly 1? Remember this grid size. The input grid size, like the real world where I shoot my waves into, this consists of a very unit size squares, green, white, green, white. Think about the non-green as well. And I started sampling it, and the sampling rate S is 0.66. Some numbers are different than others. What happens? I have my first sample points, which is first sample point is B actually, and that happens to ignore the beginning. Let's say that that's a first sample point, and notice it's a gap of 0.66, but I'm sampling something that is behaving very uniformly. It's one. Which image would you expect to happen? So I take the first color, copying it to here, next color, copying it to here, next color, and now they are distance apart, but look what happened in the sampling. I sample in the red. What is not white, what is not green is red. I sampled in the red. Next, I sample in the green, another sample in the green, one single point in the red. Red is smaller, 2 points in the green, 1 in the red, 2 in the green, 1 in the red, 2 in the green, and so on. So when you look at this image, it will definitely doesn't look like they are equally wide. At this region, green is much wider than red, and if I go further away enough, then red, this distance will appear, and now red is much wider than green. So there is something that happens in much lower frequency because these sampling rates are not to each other. That's also a good chance to ask if the sampling distance S will be larger than 1, then with a bit luck, S will be slightly larger than 1. Now it's fine. Can I move it a bit? But if it's even a bit larger, okay, I don't succeed right now, but as you can guess, if I pick the wrong side, I might miss the white completely, and then all my sampling points will be only in the red, or so on. So, you see, that's the sampling, the special frequency of the sampling, and the special frequency of the squares over here has a simple connection between them, and that's why you have strange phenomena that strips are much biased to be, at some region I'm much biased to sample inside the red instead of the green, and in some other region I'm sampling inside the green instead of the red. Oh, you know what I did? Bad. sinus alpha plus sinus beta. If you understand what I'm going to go to, great. If not, then we'll talk about it more when we'll talk about a high dynamic range. We'll go back to the special frequencies. But just to show you that you're all familiar with more patterns, even if you don't see them. Anybody remember? Formula for sinus alpha plus sinus beta. It's a geekiness competition. Remember the formula of this guy. There is a constant here, it might be 2, if I remember right. Then comes sinus alpha plus beta half. And I'm trying to think about a case that alpha and beta are very, very similar to each other, two frequencies that are very close to each other. So it's 2 times sinus alpha plus beta. I'm not done. And if alpha and beta are very close to each other, now I take the average between alpha and beta, then it doesn't really matter which one did I pick, times sinus of alpha minus beta half. I'm not sure about the half, but if alpha and beta are very close to each other, then what you'll hear over here is something that behaves as very low frequency. So if we are listening to all of it, and I have a sinus of exactly 440 hertz, and I add to it another sinus of 440 hertz, what you see here plus here, I put s to 1. F of x is 5 sinus x, g of x is 5 sinus x, and f plus g is 10 sinus x. Didn't change the frequency, nothing interesting happens. But if one of them will be of slightly different frequencies than the other, slightly different frequencies of the other, and look at their sum. And let's remove the original ones. What happens here? There is a small changes that happens very frequently. But now, since I said that alpha and beta are very small to each other, this term, sinus alpha minus beta, that's a very low frequency. It happens, it stopped happening, it happens, it stopped happening much slower. And you can only hear it back to, I think I didn't check it offline. Prove my point? You have one frequency of 440 hertz and the other one is in 441, and what you maybe hear is, oh, wow, 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 something that changed in what's the gap between 440 and 441? 1 hertz, 1 times per second or twice. Yes, sir. Am I wrong about the 2?
No, you're wrong about the second term. It's 2 sine alpha plus beta over 2 times cosine of alpha minus beta over 2. But if alpha and beta are equal, then sine of alpha minus beta is equal.
So you're absolutely right. Yeah, if alpha and beta are equal, then it should be 1. Absolutely right. But if alpha and beta are different, then that's what you hear. Something that changes in 1 hertz. You're getting the mode pattern, the same mode pattern that we saw in the GeoGebra. Now they happen in like 1 hertz. The noise sounds, but the noise in the background is still about 440 hertz, 440.5 to be precise. But the amplitude changes in 1 per second. Wow, wow, wow. Okay, and now we can get rid of it. Okay, so more pattern happens here because I sampled in the same frequency and in relationship to the special frequency of the building. To avoid it, sampled at some random locations, but still within every pixel. What a pixel, we think about it as a square, and inside the square we picked the placement of the ray exactly. Where do I place the ray? Still within pixel, and probably in more than one way per the pixel. And what would be the overall color? It's a sum of average colors that each ray gave me. And it goes on and on about still you want to have a fair sampling of every location, but you still want some randomness to avoid the Moore pattern. And the aliasing. It's also called aliasing. It's also called the jittering that we had earlier. But it's also a good way to avoid, remember, I mentioned it multiple times. If I have this black rectangle that cover this, that's one pixel with a few subpixels. Instead of, you can assign these pixels to be completely white or completely black, then it will look very jittery, and if the rectangle moves, you'll see a lot of blinkings of pixels, very annoying. Or you'll give this pixel a gray color, which is the average of how much of it is covered in black versus how much is covered in white. And instead of computing exactly what is the area that is covered in black, I'll just ask out of a few random rays that I shoot, how many hits black, how many hits white. So black and white, or whatever the RGB colors that you're doing. And you take the average of the colors from all these random things. So far, we saw that distributed ray tracing is good for two things. Avoiding Moore pattern and avoiding the jittering. Both falls under the general umbrella of anti-aliasing. This image that is over-dramatized by having the alligator itself very sharp in the reflection, or very sharp near the alligator, but things that are not in the focus are blurry, and you can just say, I'll just do ray tracing normally, and then run convolution with Gaussian to smear it, but it will not look very realistic blurriness. Same here, over-dramatized some part in the focal of the, in the white focus of the camera is very sharp. Other parts are very blurry. And you can play with it by not changing the angle of the viewing angle, not changing the camera location, but changing where the focal is. Right? Nice dramatic effect that in the same geometric scene, you can pick different location of what looks sharp and what looks blurry to keep the attention. How do I make the background here looks correctly blurry? Well, let's think about the camera location. Camera location has its focal point that says that if I'm shooting from the right distance, where the lens of the camera is appropriate, then, and this is a green object, then all these, of course, this green object shoot rays to all directions. Some of these rays hit the lens, and all the way in the right direction all accumulate to a single point, a single pixel, a single sensor of the camera. All the green object will focus over here, and if I have a red point next to it, the red point will appear on a different pixel. Red point here in the focal, when the lens is in focus, will point on a very different pixel. This sensor of the camera will get no red from this point, and the green one has only the green object followed to it. That's why the image look sharp, because there is clear boundaries between different points. What do I mean by not in focus? Here is the red object, rays emerging from it to all direction, but now one ray falls on one sensor, another ray falls on another sensor. That is, two other sensors accumulate some of the red that had the lens being focused, it will all fall on a single point. Not in focus, you're distributing this red to a lot of other sensors. That's if this object is too close, and if this object is too far from the focus, then I got the ray, hit the lens. Now that's a where I would have liked to put my sensor. Instead, I put my sensors over here. So sensor at different location of the camera accumulate some of the blue. And we want to just mimic this effect to generate the blurriness versus the focal point, just with distributed ray tracing. Right? We are moving the camera, what happens to, but looking at the same object, if we are in focal, then all these locations fall on all these different locations fall on the same sensor of the camera, despite moving. If I'm not in focus, then they fall on different location, and then when I'm doing the distributed ray tracing and doing the averaging, the object not in focus will contribute to one sensor mainly, but also to the nearby sensors to some amount. Okay, so after all this long speech, what are you doing? Instead, you are deciding about the correct object that you want to have sharp, and you can do it by, let's average a few images, shooting one ray through the image plane, and moving the objects, and only the objects that we want sharp, accordingly. So the object that we want sharp moves together with the camera, and it looks just sharp and nice. Other objects, because we are averaging a few locations of the cameras, other objects will look blurry. Exactly the same effect that you're getting if in the pre-optical sensor stabilization of your sensor phone, or shake your cell phone enough. Same idea, look at the propeller. Cool. How did we get the effect of the movement over here? You see in a few ways why why the effect is clear. The body of the airplane very sharp. The propeller looks very blurry, but it's blurry in the correct way. Background looks blurry in the correct way. Right? So it's clear that the focal of the camera is on the airplane itself. And how do you get this movement? You're just averaging a few locations of the a few positioning of the propeller. Once again, average a few locations of the propellers. So you're doing the ray tracing a few times, taking a few images, and just take the average in all of them. The airplane look exactly in the right position. The propeller, on the other hand, moved. Or the camera moved. Make sense? Same idea over here. Generating the sense of movement of the balls. How come? This part static, very sharp in the focal. This part non-static, averaging a few locations of the balls. That is, again, this image is the average of a few images, except that in all these few images, these pixels have exactly the same values in the multiple images. These pixels, each one of them, has a value which is a sum up of a few balls that falls on its location. Make sense? Clear. Good. Same for motion of getting the motion blur by averaging a few locations of the cue balls. And we're done with this part. Now to download the next. Switch started to change its policy and give me a hard time storing the image, storing my videos. So some of them I moved to my private YouTube account. They are accessible, but I didn't put any link. I'll arrange them a bit later, or just Google for my link. Like the recording are still visible for a while, but I cannot store them anymore long time. Twitch changed its location, its policy about more space completely. Okay, we start speaking about hidden surfaces removal, making this looks like a 3D scenario. And in all the discussion about the 3D surface illumination, I'll assume that I don't use perspective projection. It's not that the eye is relatively close to the object. The eye is still relatively close, but at the same time the eye is in infinity, so your object just falls as a parallel ray. If you do the ray tracing, you just from every pixel shoot a ray, but all these rays are parallel to each other. So all these rays are parallel to each other, and all of them are going toward the negative z direction. As opposed to these figures that I made, they're actually going in the positive z direction. So I'm going to describe a set of algorithms that assumes that I have perspective projection, but that assumes that I have orthographic projection. Just an object A just project onto the image plane by remove its z value. So A that has coordinate 7, 7 just falls on pixel 7. So it looks very limiting, but am I going to describe a set of algorithms that works only for orthographic projection? Absolutely not. There will be one magic matrix that will come and take the perspective transformation into orthographic one. But the algorithms, especially if we are using hardware for part of them, would much rather assume that by working on depth, which object occludes which other object, I only look at the z coordinates. And the z coordinate is just a z coordinating of the point. Okay? And I use the term depth a lot. So depth here means from the image plane, from the pixel, if you're doing ray tracing, how long is the ray until I hit this point? So if I hit this point at z equal -7, and the image plane is at 4, then I just measure the horizontal distance from the pixel until it hits a point. That would be the depth of this point. Sounds very awkward, very. So when I understand, depth is nothing but how far away from the point this object is, but I will use the depth as a number. How far away you are from the pixel, and assume for simplicity that all your rays are parallel to each other, are all into the -a. So the location of the eye is not in the game at all. Again, I don't need to tell you where the eye is. Once again, we have a cube, camera, and projected space. That would be with perspective projection. And you see the nice four-stone, the pyramid. Objects are here, and inside it, I actually do want to assume that it is perspective projection, but before I actually read the object, I'll apply some magic transformation, and now all my rays, all this four-stone is warped, massaged, and now the two walls of the four-stone are parallel to each other. So from pyramid, it's becoming just a box. And now all my rays are parallel to each other. So that's the object, right? That would be its perspective image of the wireframe, and maybe that would be the orthographic projection of the same square, of the same box. Everybody needs a refreshment about orthographic projection versus perspective. What's the difference? cool with everybody, right? Perspective, I assume that the eye is at infinity. Even though I'm looking at one object of the plane, in particular, if I have one part of the cube that is further away, has different depth than another part of the cube, they will appear, if they have the same length, these edges have the same length, they should appear at the same length of the image. Even if one edge is much further away or has much higher depth than the other one. Okay, so hidden surface removal for polygonal scene, meaning all my objects are polygons, input a set of polygons in 3 dimensions, plus the viewpoints, if I do have, and the output would be the 2 images of the object polygons, but only the regions that are visible should be displayed. Okay. Orange occludes from the viewer part of the red, so I need to remove from the red part, and that's how you have the image, the mental image of the 3D scene, because you see what occludes what. And together with perspective and various other clues, you can decide what happens in 3D. So, hidden surfaces removal. Hidden meaning, for the review right now, this portion is hidden. Removal, so only the part that are observed by the viewers, and I assume that any object right now in this lecture is completely opaque. Nothing transparent, nothing semi-transparent, no alpha, no blending of a few colors. If you have one triangle, the green triangle, the green square that occludes the brown square, then part of the brown square should be removed completely opaque. And the first trick is, how do I notice that there is a triangle that I shouldn't show you? Everything is polygon, in particular, everything will be triangles. I want to have a quick check to say, there is a stream of billions of triangles. Some of them the viewer doesn't see. Why the viewer doesn't see? Again, assuming everything is opaque, because the face of the polygon of this triangle points away from the viewer. The viewer is somewhere here. If it's opaque, there should be another triangle that occludes the face, because it cannot be that you see just the back skin of the triangle, but not, it must be occluded by another skin. So using the normal of the triangle, I can have a very fast test to avoid rendering some of the triangles before I actually check any further data about these triangles. How? I just by looking at these 3 vertices. We'll talk about polygonal mesh. How do I assemble the skin of the object all over the place? But this trick called a polygon culling, not a term that as a vegetarian particularly like. Triangle culling meaning filter out triangles that you don't need to have. How? Look at that normal, but the normal now will make sure that when we are looking into the triangle, its vertices appears in a counterclockwise order. So this triangle has 2 normals, but the only one that we formally treat as a normal as the one from which, if you look at it, then you see from your side, it will be in this counterclockwise. From your side, it would be, so, I'm not smart enough. If you look at the vertices, if the triangle is relevant to you, then you see its 3 vertices in a counterclockwise order. How can I check quickly if it's a counterclockwise order, that is, the normal points toward me? I'll look at, when I store the triangle, I'll make sure that I store them in counterclockwise order. So what happened when I watch the same 3 vertices, but from the opposite side, the normal points away from me? What I'm trying to say is that let's look at the order of the vertices as they appeared when you read them in the file, in the array. That you see your graphic display. See the three vertices at this order, V1, V2, V3, counterclockwise. It will check what are their normal, computing the dot, the cross product in this direction, and look at N, the unique normal, given that that's the input, the unique normal, ignoring the other normal, and multiplying it by direction to me. If I see this triangle, then direction to me times this vector, cosine of the angle, should be, like, here is a viewer. Obviously, I did not put that. Here is a viewer, here is my triangle, and the normal to the triangle from the opposite direction. What is a cosine of these two numbers? This vector times this vector should be dot product. This vector times this product. This vector should be, if the viewer sees the face of this triangle, help?
Negative.
Should be negative. If it's positive, that is, here is the viewer, direction from the viewer to the triangle, normal from the surface, that is, to see this triangle, I need to stand over here. Normal is this particular. This is the direction from the viewer to the triangle. Angle between them, copy N to here. This angle is smaller than 90, so the cosine should be positive. So N, where the vertices comes, it's a file times direction from the viewer. If the product is negative, don't worry about this triangle. The viewer doesn't see it. So that was just backface Hewlett. Okay, this is the opaque object. Faces that are away from the viewer are occluded by faces that point toward the viewer. I think that the more I speak about it, the less obvious it will be. Cool? Okay, backface. Fueling determines if N dot product V, and in a convex object, of course, invisible back faces and all four faces are refers to. Okay? Non-convex, still you might have back faces that are still invisible for one object, or let's skip through this slide, doesn't matter. Depth sorting. I want to describe the first algorithm for hidden surfaces removal. Is this algorithm very practical? No, but it gives some good idea for algorithms that are. So that would be the beginning of the painter algorithm. So what I'm going to do is, given this set of polygons, triangles, sort them according to the depth. Okay, and possibly this order is not necessarily unique, but I want to say that if an object that is further away from you, the viewer, should appear somehow later versus an object that is closer to you. This is sorting. And if you have two objects that none of them occlude the other, then this order is just not unique. And now, what the painter algorithm tells you. It says that the painter algorithm says that when it works, it's extremely simple algorithm because it solves the hidden surfaces removal automatically. What happens here? It will work in an example like you have a few windows open, and between which object, which window occludes which other window defines a nicely ordered order. But closer to you from the viewer point, it doesn't matter exactly what is the depth because it's not perspective projection, but it's clear who comes in front of whom, and this is an example where the painter algorithm works very well. So let's see the painter algorithm. Here is set of objects. I first render the one that is the furthest away. That is, I set all the pixels that falls into this polygon to be white. Why? Because they are the furthest away from the viewer. Here is an object that is a bit closer to the viewer. Had I cared about hidden surfaces removal, I should have taken this polygon and partitioning it into 3 pieces, 2 pieces that you see and 1 piece occluded that you don't see. Painter algorithm is a pain-free algorithm in this part. I don't worry about it. Instead, I just sort them in the right order. I had all the pixels change their color inside this rectangle to be white. And now I set all the pixels inside this one to be red. And the order matters. Which order is this? From the furthest away to the closest away, from your perspective. So some of the pixels were black, now they are white. Some of the pixels were white because of being inside this one. Changing to red, I don't care. Red is closer, so all its pixels are driven. And I don't need to solve the hidden pixel removal. Another object comes, all its pixels change to whatever its color, and so on. Okay, so draw one primitive at a time, starting from the furthest away one that I don't know if it's furthest away or not. Between this one and this one, there is not clear order because there is no occlusion between them. But this, I could have started from this one and then moved to this one. So between these two, I don't know the exact order or don't care about the exact order. Same actually between these 3. Now, between this face and this face, there is clear order. This face occludes this face, so this face should be rendered only after this face was rendered. Now the order does matter. The same goes about the order between this one and this one. This and this one and this one, I don't care. But the order between these pairs are well defined. Next one, again, change all the pixels to be inside this face. And finally this one, the last object. And the 3D structure is clear to everybody. That's very nice, and when it works fantastically. And very quick, because every pixel just cares about its own shape. You don't care about what occludes it later, what we'll draw later. So when will it not work? Of course, if I have 2 angles that intersect each other, then I'm in troubles. Then the painter algorithm does not work. We talk about painter algorithm also in computational geometry, so please don't answer. What happens if my objects don't intersect each other? It is clear that I have a well-defined order between them. It occludes which one occludes which. They are disjoint. I don't have any point that lies on 2 polygons at the same time. Here is a set of polygons where no point in 3D. I don't have these 2 polygons are disjoint. I don't have a point that lies on these 2 polygons at the same time, 3D. Does it mean that I can render them using, and they're both convex even, and there are only 2 of them. Can I render always both of them with correct hidden surface removal for 2 polygons? Yeah. Whatever it happens, if they are convex and each one is planar, there is nothing bad that can happen. What happens if there are 3? Somebody?
If they're still disjoint, it'll work out.
Sorry?
If they're still disjoint, it'll work out with the painter's algorithm.
It was my answer as well. I get to know. So these 2 are disjoint, and these 2 are disjoint, and now I created. You see it? I created a cycle. At which order should I try? Remember, what is the furthest away from you? It's tempting to say this one is the furthest away because it's behind this one, but there is another point where this guy comes before this guy. And there is a point where this one comes before this one. If this monochromatic example confuses you, let's take Blue, red, still, so far everything is fine. And now, am I good? Now I'm good. What is from which object should I start? Should I start from the red? No, red occludes at some point the green. Should I start from the green? No, because at some point green occludes the blue. So should I start from blue? No, because there is a point that blue occludes the red. So there is no clear order between them. So that's an example where the painter algorithm of sorting them in the right order and draws them according to the order will not work. Right? This is just this example. There is a cycle. Of course, if the objects are not disjoint, then it's wrong already. What does it mean? What should I do if I do want to use the painter algorithm for these objects? Is it still doable? Yes, but then I need to take this triangle and split it into two sub-triangles. I need to cut them in between. And maybe I need to split the slivers, the resulting fragments of this triangle into sub-triangle, and so on and so forth. So the same goes here. That would be another example of meditating over the hidden surface removal. Does it still make sense to do? To some extent, yes. To some extent, no. You still want to find the order. It will help you in many cases, especially if you're using our next topic, binary space partitions. But to take triangles and see results of triangles and results of splitting triangles, that will not work. It will, doing computation, you'll get computationally with something like n squared. If you live in 3D, you can easily get n squared or even n cube if you're not convinced. Many sub-triangles, if you start from n triangles and you start chopping them into sub-triangles. So what would you do? It would be our next algorithm, which will be use a z-buffer, which is what? What is a big difference? That the image that I want to generate doesn't care about the details, every piece that you see or don't see, in infinite resolution. You watch the image via only these many pixels, and as long as I'm correct about the pixels themselves, and let for each pixel deciding what the object with the minimum depth that the pixel needs to see, I can do things much faster even with a single CPU. That would be the z-buffer algorithm, which is quite fast even in a single CPU, and it's much nicer to be parallelized if the same algorithm and start replacing pieces of it to implement in hardware, which will make it way, way faster. And now things starts to be interactive. Otherwise, your chance of having interactive scene in 3D is unrealistic, unless you're talking about really special scene. Let's go again to what case I don't need to worry about the order. Like how to see a few windows that are open. The exact z value of each window doesn't matter, but the order between them is, you can assume that you have it, and that, yeah.
So would you render the this image with the last window first and paint all of the pixels and then overwrite every time? Or do you go front to back and then you just mark each time?
Great question. Intuitively, we all, at least my visual guess is, let's decide about a large object closer to the viewer and walk our way from the closest to the first array and see if we need to change something. The opposite of what the painter algorithm tells you. Painter algorithm starts from the back ones, and then you're guaranteed at least not to make mistakes as long as the order between them is well defined. You can only need to apply your sorting algorithm and see if the sorting algorithm complains. Can you sort the graph? Actually do topological sort, because the order is not necessarily unique, but you can still find who should come before whom, and if you are getting from the graph if you are finding, trying to ask if the graph is a DAG, directed acyclic graph. When I'm pointing from one object to an object behind it, behind meaning there is at least one point that this object comes behind it. This will be a graph. Why is this a graph? Because every triangle, T1 will be a node, T2 will be a node, and I'll have an edge from T1 to T2 if a point of T1 occludes a point of T2. And if a point of T2 occludes a point of T3, then there is an edge from T1 to T3. Now, let's draw this graph in the case of the cycle that I just showed you. Right? There is an edge from whom to whom. Then there will be an edge from T1 to T2, T1 there is a point that T1 occludes T2. There is an edge from T2 to T3 because there is a point that they occlude, but there is also an edge from T3 to T1. So this is not a directed acyclic graph. Namely, if you sorted the object and your graph is a DAG, directed acyclic cycle-free graph, then Painter algorithm works perfectly fine. Not about the running time, but at least in terms of no errors in the rendering. If your graph contains a cycle, then you need to start splitting objects. Okay, now, did I answer? It doesn't mean that, so for here, in the case of just rendering the window, it looks perfectly fine for me. I don't know if every monitor will do it, but at least it's small number of objects, the order is clear, and there is nothing topologically that happens because obviously I cannot create cycles when all I show is windows on my monitors. Binary space partition, big topic. So, binary space partition is any tree where I have a set of objects for when my slides are two-dimensional, so I'll assume that the objects in the example are in 2D. It's, of course, you use BSP when your object is in 3D. And now I look at the set of objects and ask, can I find a line L1 that split my object? That is in this thing that you see over there. You identify the line L1 as something that you'll keep as the root of the tree. And now some objects are above this line or above a plane in 3D. Some objects are above this line, and some objects are below. So in particular, in this example, if I think about O4 and O5, O4 and O5, these two objects, they are both below. So I'll store them in the left subtree. And in the right subtree, I'll store everything that is above this line, which would be O1, O2, and O3. So that was the case that I found a line or a plane that completely splits the object, and I don't have any objects that cross the boundaries. And now look at these three objects, O1, O2, and O3. Let's meditate only on these three objects, because now I continue building the tree recursively only for these three objects. So for these three objects, I realized that L2 is a descent line. Why is a descent line? Because it splits at least some of the objects away from each other. At least O2 and O3 are now separated once I placed L2 at this node. Okay. Once I'll split via L2, then now to the one side of L2, you have the whole O2 on one side of O2. O1 will go to another side, so O1 will be here, O2 will be here. That's about L2. And now let's think about L2. L2 is a line or a plane, so it goes all the way from infinity to infinity, like every line that respects itself, except that its effect as a navigator, go left, go right, or render this or render this, its effect is only limited to the part that the BSP already told me. You decided to go to the part of 04, 05, or 04 and 5, that is, to the part that is below L1, 04 and to the part that is above L1, or 1, or 2, or 3. So L2 as a line, even though it goes all the way to infinity, its impact is only for the portion of the plane that is above, above L1. Okay, and that's why I rendered L2. That's why I rendered L2 only on the way until it hits, it's shielded by L1. Now, so it split O2 into one side, O3 into the other side. What happened with poor O1? Well, L2 split it into two sub-portions. What does it mean? I don't necessarily need to really keep the two different fragments, but I do need to store O1 both as a subtree, both as in the left subtree of L2 appears O1, and O1 appears once again. And so on. And now we continue. We'll talk more about geometric data structures. BSP is a very general term. We'll talk about a few BSPs that in addition have separate points. BSP just means it's binary and it's hierarchical. So taking the whole space, split it by a plane, split each piece by a plane, and so on. Same intuition, L4 is a descent line, but its effect is only to the part to the above L1 and above L2. So L1 I just showed as the region of impact. Otherwise it would be very confusing. Great, so I got this BSP that I completely hand-waved through, very confusing through, but you understand that there is some BSP involved. And let's assume that I can, again, not people that took computational geometry. So you have S1, which is set of obstacles, all below L1, and you have S2, capital S2, a set of obstacles which are all above L1. And how did I pick this line in an efficient way? It's a whole theory by itself. I will tell you how do I pick these lines, but I want to talk about the painter algorithm. So you see this image right here. So S1 would be 04, 05 or an O5. And S2, the other set of obstacles, will be these objects. And my big question is, how is this related to the painter algorithm? How can I, and assuming that these trees continue recursively until at the very bottom line, what I have at the end, I'm just left with one obstacle per leaf. And now tell me, if I did, assuming that I built a BSP and I never needed to split any object, can I use the painter algorithm without any errors? And if yes, how? I built a BSP. I never had to split any objects, any triangles. So every such, the triangles that you see on the whiteboard, that's just a recursive subtree that I built for the object based on L1, just continue recursively. The same goes for the other subtree. Everything works perfectly, and you are ending up with one object per leaf and no objects participate in two leaves. And my question is, how would you how would you use it for the painter algorithm? So again, just to render the same pictures that we had on the whiteboard, I started from L1, and here was here was S1, set of objects, triangle. Here was S2. And I also told you that there is a viewer in the game. Here is a viewer. At which order should you render the object so it looks good to the viewer? So all the hidden surfaces are well treated.
Bottom to top.
From bottom to top, I have this tree here as a viewer for in this geometric scene, 2D only, but for this geometric scene. Oh, in the case of this tree, the viewer is where I put my finger. I want to use a painter algorithm to render all the objects, and I want to do hidden surfaces. You know, I don't want to worry about hidden surfaces. I just want the tree to tell me at which order to render them. You took computer. Did you? You took something. At which order should I render them, if at all? Here is my finger. And will it change if, say, the viewer is right here, on the other side of L1? What should I do if the viewer is here? Render all the objects at which side? You are checking where my finger is with respect to L1. Let's say that the viewer is somewhere, what would it be, next to O1. Viewer is next to O1. So here's the viewer. I go to the tree, and I find out where the viewer is, and what are the first objects that I rendered. The ones in the same subtree as the viewer? No, that's the opposite philosophy. They're closer to the viewer, but the painter algorithm says, no, you are reversing the order. Start from the ones that are furthest away. So if the viewer is here, then you are going to this subtree, and you first render all the objects of S2. The subtree not containing the viewer is where you start from, and after you rendered all the objects of S2, then you can render all the objects in S1. But S2 and S1 might be a big sets each individually, so at which order should I render this object? Recursively. But now I'll check how the viewer is with respect to each node of the tree. And for each one, first render the ones that are furthest away from you, then the ones that are closer to you. We have it all. Quad trees that we'll talk about much more are a good example of BSP. by the way. We'll talk much more about quad trees. Cases that it doesn't work. And here is a viewer. Let's with a few cases. We want to first render the ones, if this is line 0, first render the ones that are furthest away from the viewer, that is to the right. If the viewer is above line 0, you'll render first C, D, E, and after rendering them, you'll render A and B. At which order will you render C, D, and E? Again, the BSP will tell you how to continue at each moment. So once a BSP is given, if the BS3 doesn't have any objects that appear more than once or nearly doesn't have it, then you can always use a BSP, and it's very practical for interactive games. The viewer wants to move, great, you're just changing the order at which you're rendering them, but you don't need to do anything to the tree. The tree stays the same tree, no matter where the viewer. So once again, the process as we think about it in time is, I have my set of obstacles static at the moment, that is, obstacles don't move, I don't add delete obstacles. I build, for a given set of obstacles in 3D, I'll build the BSP for them. I'll invest some time in building the BSP, but then in return, no matter where the viewer is, by just traversing the tree, you can render everything for the viewer without ever worrying about hidden surfaces removal. And once again, hidden surface removal is a big, big problem. It takes a lot of time. I have to solve it. BSP solved all of it and tells me always, here is a nice hierarchical partition of what is furthest away from the view right now, where I saw small closer. And if it's a interactive video game, it's great. The viewer, the player moves, you are just changing where you are in the tree, but the tree stays the same. Make sense? Even though I didn't tell you how to build a BSP? Cool. You try to ask something, but I wanted to. Okay, good. Okay, thanks. And you have until Friday-ish. Assume now that it's Friday. Right? If there will be a screen, then there will be a screen, but we still have 6 homeworks and building and stuff. So don't over. At the moment, we are assuming it's Friday, hard deadline.